doing well. So, questions? One at a time. All right, so today's ODP, and I don't think I'm going to post one tomorrow, so same as yesterday, except your hash function takes a second argument, which is a probe. So there's some samples for you. If you say hello with a probe of 0, you get a hash value of 4. If the probe is 1, you add 1 to that, you get a 5. If your probe is 2, you add 2 squared is 4. 4 plus 4 is 8, and so on. So it's essentially the same thing as yesterday's function. All right, so there's a way to do yesterday's hash. And go through each character in the usual for loop for traveling down a string, add up the characters to a running sum, reduce mod 31. You can reduce mod 31 either here or you could do it here. Right, 215 modular arithmetic, we've learned that you can do modular stuff wherever you like. A plus B mod 31 is the same as A mod 31 plus B mod 31. The advantage of doing this is that the thing you're adding is never bigger than 30. Right, so if we added a billion numbers, potentially we could overflow the size of an integer, and that might do weird things. But like this, each number we add to our sum we reduce, we know sum's never bigger than 30. That's the same thing you do with pencil and paper when you're testing a prime number or doing crypto. You reduce as often as you can so the numbers you're working with are small. So we're helping the computer have a better day. All right, so good on 214. And I had a typo in the configuration this morning, so the first few people who tried to assess it got 0, so I fixed that and posted that announcement. It happens sometimes. All right, well, so we talked about hashes for a few days, and we're going to kind of leave that for now, and I still don't know if PA3 is going to be hashes or stacks and queues, but we're going to go on and we're going to talk about stacks and queues. So these are two data structures that pop up all over the place in computer science. Stacks you encounter if you've done Engineering 270. You encounter a stack when we do calls or when we do interrupts. There's this thing called a stack that's used to remember what we were doing when we get interrupted. I think I mentioned if you play old style Magic, there was a stack, actually it's still in the terminology, there's a stack where you put spells on and they resolve in reverse order. Stacks pop up in sort of our daily life all the time. If you hear geeky people talking, sometimes they'll talk about their stack overflowing. And it happens when you're trying to remember what you were doing and you get interrupted and you have to remember something else. And if you get too many of those things, you forget what you were doing and your stack just overflowed. The general notion of stacks and queues and where they pop up, say in operating systems, is you have a series of things that you're trying to remember. And something happens, you need to remember it because you're going to deal with it later. For example, you're running some code and there's an interrupt. Something happens outside the system that says, hey, I need the computer's attention. Stop what you're doing and come deal with me. You need to remember what you were doing before you go deal with something else. And you're dealing with that something else and another interrupt occurs and says, hey, stop what you're doing, come deal with me. You've got to remember where you were over here to deal with this new thing and then go back to that thing. And then when you're done with that thing, you got to go back to the original thing. So you have to remember multiple things. And sometimes you want to remember these in the same order that they occurred and sometimes reverse order. So for example, you have a computer and if you run the top command, it tells you what's going on the system. This will tell you that there are 253 tasks running on this machine right now. 198 of them are sleeping. I've got 2 zombies. I didn't know that. And I've got 1 process actually running. When a job needs the CPU, it says, hey, give me some CPU time, right? You've got 20 jobs that need the CPU. They're all waving their hands saying, give me some CPU time. Okay, what does the system do? It gives this job a little bit of time, and then it gives the next job, and then the third one, and the fourth one, and the fifth, and the 20th, and then it goes back to the first, gives that more time, right? And while it's doing this, if a 21st job says, hey, give me some time too, right? After it finishes that 20th job, now it gives some time to this new 21st job, and then it goes back to the beginning. So we're adding things into this. When a job finishes, it doesn't need time anymore. We take it out of this collection of job information. But we have this collection of clients that need service, basically. And in this case, we're processing them in order, in the order in which they arrived. And when we're finished processing a job, and we've given it a little bit of time, we put it into the back of the list. Okay, so these are instances of stacks or queues. I'm curious where my zombies are, but I'll find them later. So let's look at some specific examples. So classic example of a queue is the checkout line at the store. So here's the cashier. And customer 1 arrives, and there's nobody in line, so they go up here and they're being managed by the cashier. They're scanning their groceries, scanning their card, and so on. And while customer 1 is checking out, customers 2 and 3 arrive, and they queue up behind customer 1. Okay, customer 2 arrived first, and then customer 3. So when the first customer is done, which customer gets taken care of next? Customer 2. So they move up here to position 2, and third person moves up. And now customer 4 arrives, and customer 5, and customer 6. And no matter who else arrives, the next customer who's going to be dealt with is customer 3. Right? They're sitting at this second spot in this queue, and when 2 is finished, right, 3 will get taken care of next, and then 4. And customer 1 forgot something, so they go off and they get some milk, and they come back and they go into the back of the line, and now they're sitting over here. Okay, this is a queue. And so a queue we can think of as a pipeline, and it has 2 ends. We call this end the head, and this end the tail. And things go into the tail and they come out of the head. And the general flow of information in here is first in, first out. The first thing to come into this pipeline will be the first thing that comes out the other side. And so another name for a queue is a FIFO, first in, first out. And this can be used to keep track of customers in a line. This can be used to keep track of jobs in a process execution queue. And some people who are very organized, they live their lives according to a queue philosophy. So what does a day in the life look like if you have a queue type brain? So you're doing homework, and the phone rings, and so you remember that you're going to check your phone for messages, but you're going to do that after your homework's done. And now you get hungry, so you're going to eat some food, but you're going to do that after you're done with your homework and after you check your phone, right? And now the cat knocks over a candle and the house is on fire, and so you have to put out the fire, but you're planning to do that after you're done with the homework. You check your phone, you eat your food. Okay? So you're doing things in the order in which they occur. Okay, that's a queue-based thing. And it's not how most of us work. Most of us tend to work with what's called a stack. And a stack is a last in, first out. Whatever the latest thing is that goes into the stack is the first thing you deal with. So what does a stack look like? Well, you're doing your homework, and the phone rings, so you stop doing your homework, right? You pause this, and you get the phone. And when you finish dealing with the phone, when you're done talking or checking your messages or something, you go back and you work on your homework some more. And now you get hungry, so you pause your homework and you start eating food. And while you're eating your food, the cat knocks over the candle and the house is on fire. So you stop eating your food and you grab the fire extinguisher and put out the fire. And then when you're done, you go back to eating your food, and then when you're done, you go back to working on your homework. Okay, so you're processing things in the opposite order in which they occur. The latest thing that occurs, that's what you spend your time on. And if something occurs while you're doing that, you go ahead and you pause what you're doing and you deal with that latest thing.
Is the stack what function calls use?
Stack is exactly what function calls use. Right, and this is the most common use for a stack inside a computer, is you have a program. Here's a main program and it's doing some stuff and it says call function 1 and some other stuff, call function 2 and return. And function 1 says do some stuff, call function 2, do some stuff, call function 3, and then return. And function 2 does some stuff, and function 3 does some stuff. So what does your process look like? Well, you start off here, you come down, you get to this thing that says call function 1, you jump over to function 1. You come down here, it says call function 2. Okay, stop what you're doing. I know you're running function 1, but stop doing that. Go and call function 2. Run through all that code. When you're done, come back to where you were and continue. Oh yeah, I was doing function 1. Okay, I'll keep doing that. Up here's a call to function 3. Hop down to function 3. Finish that. Come back up. Finish function 3. There's our return. Now we come back to here and continue with our main program. So where's the stack used? The stack is how you remember where you need to return to when you're done with the last call. So we remember this address on our stack. So let's call this location A. So location A goes on our stack. And we jump over to function 1. And we get this call location to function 2. So this instruction after the call B, we put that on our stack. And we call function 2, and at the end of function 2 we have a return. What's the last thing we pushed on our stack? That was B. So we get rid of that and we go back to B. And we continue and there's a call to function 3, so we save this location C on the stack. Do function 3. When it says return, we come back to location C. And then we keep executing until we get to a return. Where do we return? What's the last thing on our stack? A. So go back to location A and continue.
Return, go back to location A, and then keep going, and then it's gonna hit function 2.
And then it's going to say call function 2. We're going to take this location of the next instruction D, put that on the stack, and jump over to function 2.
But we already function 2 before.
Yeah, we're doing it again. Yep. So we'll come down here. I'll change colors. We'll come down here, call function 2. Down here, we get to the return statement. Where should we return to? We should return to D. So we come back here, and then there's a return statement. And our stack probably had, something on here like the operating system location that we used when we called our main program. So this returns back to the operating system now. So if you've done 270, this is probably familiar to you. If you haven't, it will be. But that's the main thing stacks are used for, is call and return. And like I say, we use them in life because we usually work in an interrupt-driven way. We do something, and then there's a lockdown drill, so we stop what we're doing, we deal with the lockdown drill, then we come back and continue where we were. So the stuff we were doing goes onto the stack, right, and then it gets pulled off later. So in a queue-based system, because there are queue-based systems, we don't usually work first in, first out, but sometimes we do, right? So if I'm helping people in my office hours, that's more of a queue setup than a stack, right? A stack would be kind of counterproductive because every time somebody came by with a question, I'd stop what I was doing and answer this new question. And the first person who showed up at 8 in the morning, I'll be here at 8 tomorrow in the digital lounge, by the way. First person who showed up at 8 would probably never get my attention because everybody who comes along gets my attention and they leave and somebody else comes along and so on, right? So usually I would be working with a queue model. And so student 1 shows up and I start helping them, and student 2 shows up and they queue behind, and student 3 queues behind. And while I'm helping student 1, the whiteboard marker fails, runs out of ink. I probably would not put that at the back of the queue and say, okay, well, I'll get a new marker after I help students 2 and 3, right? That's something that's a higher priority, because we can't work on the board anymore without a whiteboard marker. So getting a new marker would go into a different queue with a higher priority. So I get the marker, and then when I'm done, I go back and I continue helping a student. Or there's a lockdown drill while I'm helping student 2. I can't say, okay, hold on, I got 3 more students to help, and then we'll deal with the lockdown drill, right? So we can have different priority queues, and this happens inside an operating system also. So if you look at the list of jobs, some of these are owned by Nick, and the priority, that PR shows 20, that's actually a low priority. Some of these are owned by Root, and they have a priority of 0. That's a very high priority. So even though, imagine there's a single CPU, so it's only doing one task at a time, even if I'm due for my turn at the CPU, if this higher priority job also needs a CPU, it'll get the attention first. So there's multiple queues, and there's actually a different queue for each priority level. And you can set the priority of jobs. If you're doing something that isn't time critical, you can give it a low priority, which is a high number, and it will get time when nothing else that's more important needs it. So priority queues we'll talk about in a few weeks in detail when we talk about heaps, because heaps are a way to implement priority queues. And they're also useful for doing some graph things like Dijkstra's algorithm if you've done 215 already. All right, so that's sort of a high-level view of stacks and queues. And I'll just mention the way that I was introduced to stacks. I don't know if it's useful or not, but it's the way I think of stacks in my head now because I was introduced through this. You go into like a Chinese restaurant or some kind of buffet, right? And there's this machine in the beginning that has plates. And you take a plate off the top, and magically another plate pops up in its place, right? So there's a spring-loaded system, and there's a bunch of plates in there. And you take a plate, another one pops up, person behind you takes another plate, that one's wet, so you put it aside, you take another plate, and these new plates just keep appearing. And then every now and then, dishwasher comes out from the back with a whole stack of plates and puts them on top of this thing, and they all sink down, right? The last dish that they put into that machine, that's the first one that somebody's going to take. And the first dish that they put on, the one at the bottom of that pile, that's the last one somebody's going to take. Okay, that's a stack structure, last in, first out. And if you take a plate and find out you don't need it and you put it back down on the top of the pile, that's going to be the first one that somebody takes. So that's kind of a physical model. Okay, so let's talk about queues first. So remember, it's this pipeline's got a tail and a head. We insert to the tail and we remove from the head. And there's some ambiguity in the literature about what the tail is, what the head is. This is the more common interpretation. This is the one I'm going to try really hard to stick to with absolute consistency. So we insert at the tail, we remove from the head. But if you swap your definitions, the concepts are the same, but your answers are always backwards. Okay, so what does this look like as an abstract data type? We're going to talk about different ways to implement queues, but let's look at it from a user perspective. You're writing a program that's going to use a queue. You don't care how it does this first in, first out behavior. So what does your interface look like? As usual, some kind of initialization, something to give you an empty queue. Some way to insert data into the queue. And I'll just add a comment, insert adds to the tail. Some way to remove. From the queue. And we read from the head. Some sort of function that tells us whether or not the queue is empty. And Boolean is pseudocode here. We don't technically have a Boolean in C, but we use integers for it. But an isEmpty function that we give the queue, and it tells us is there anything in the queue or not. Because it's not like an array where, you know, if the size of the array is 0, you know there's nothing in the array. Or if your index is negative, you know that you're outside the array, right? So you're adding stuff, you're removing stuff, they're not necessarily synchronized with each other. So we want to be able to go in and say, is the queue empty? Okay, and then possibly we want to have some kind of is full. Because depending on how we implement this, it's possible that our queue is going to not be able to store anything else. Well, kind of regardless of how we implement it, because it's going to take memory to store stuff. So we might not have any memory left on the system to store anything more. So we want to know if something's full before we try to store something else. Yeah?
The third line where it says data equals remove queue, the comment, does that say read from head? Or
Yeah. Yeah, so we take things out of the head. So we're picking up whatever's on this end of the queue. When we insert, we're inserting into the tail end. And there's different ways you could do this, right? When you remove from the queue, we could somehow return a flag like null to say there was nothing in the queue. Or when we insert, we could return a flag saying, did we succeed or did the queue end up being full? And we couldn't insert. But it's nice to have these helper functions anyway. But something like this, or maybe a small subset, is pretty much all we need to interact with a queue. And with this kind of interface, it makes no difference to us how the queue is actually implemented. Now there's a number of ways we can implement it. A linked list is a really easy way to implement a queue. because what's a list? You can just keep adding things to it. You can remove from anywhere you want. So our insert might just put something in the very beginning of the list, and when we say remove, we just move down to the end of the list and we give you whatever the end thing is, and we delete it from the list. And if we have a circular list, it's really easy to get to that end piece. It takes one step. So that's a very efficient way to implement a queue, but it takes a little more memory and housekeeping because you've got linked lists with pointers and stuff like that. We can also implement a queue with just an array. And that's more space efficient, but it takes a little more time to do things, but not too bad. We could also implement it with magic gnomes and unicorns. And it shouldn't make any difference to the user as long as this is their interface. So you say insert queue into a data and it sends a message to some foreign land and there's a gnome who writes your data down on a stone. Doesn't make any difference to us, right? That's the whole idea of an abstract data type. Alright, so that's a queue. Let's look at a stack. So again, there's some kind of a net. When we put something into the stack, usually the terminology is push. It's basically an insert, but typically we call it push. But this is really an insert. Or an add to the top of the stack. So queue, we have terminology, which is the head and the tail. With stack, we usually just talk about the top. So here's our stack. And this is the top. And this is where we insert, and this is also where we remove. So think stack of dishes again, if you like. So push, or pushing down, right, is putting something in here. When we want to remove something, that's usually called a pop. So remove from the top of stack, which is usually just TOS. Mm-hmm.
Is this the same thing that we learned in Engineering 270?
Exactly, yeah. It's the exact same creature. And again, we'd like to know if the stack is full, because it can only hold so much stuff. So before we push something on, we want to make sure there's space for that. And it's helpful, but not always necessary, to know if it's empty. But usually, we can tell if it's empty. For most things that we do, like if you're using a stack to store calls and returns, there's no need for an is empty, because it should only be returning if you did a call. If you try to return but you didn't actually do a call, if you're inside a thing that wasn't called and you say return, you're going to try to pop something that's not there. So popping from an empty stack is an error condition. So that's a sufficient set of routines to interface with a stack. There's also some other terminology that comes along with stacks. So an overflow is when you try to push something into a full stack. So Stack Overflow, the website, right? That's what an overflow is. Stack Overflow is a classic error in operating systems. If something goes really wrong, if your code has an infinite loop that keeps calling itself, it'll eventually get a stack overflow, because you're trying to remember all these return locations, and at some point you can't remember anymore and your stack blows up. So overflow, trying to push to a full stack. The flip side is underflow, which is trying to pop from an empty stack. So again, engineering 270, there's the stack pointer register, and it has 2 bits in it associated with overflow and underflow. And those can get set if you do a pop or a push when it's empty or full, respectively. And stacks can be implemented lots of different ways. Really easy to implement with a list. So how do you do it with a list? Well, when you push, you simply add something right after the sentinel. If you have a sentinel, you put something in the beginning of the list. If you push another thing, you put that in the beginning of the list, and the first thing gets moved down, and so on. When you pop, you just remove the first thing in the list and delete it. So easy implementation with a linked list. Also really easy to implement with an array. With an array, we're going to need something that tells us where we are in the array. That's the stack pointer. Also a 270 concept. All right, questions up to here. You got the high-level concept, queues and stacks. So let's implement. And let's start with queues. And queues are a little nastier to implement than stacks. So we'll start with the worst one, and then we'll relax tomorrow. So we can implement with an array. So let's, again, we'll just pick on integers. We're going to make a queue of integers. And I'm not going to be very generous. I'm going to make a queue that can hold roughly 10 things. So with an array, there's always this problem that you're putting a limit on how big the thing can be, right? Arrays are a fixed size, typically. With a linked list, it can grow and shrink until we run out of memory on the system. With an array, like in a hash table, if we make it 10 elements long, that's all the storage we got. So I'm going to make my queue is going to be the name of my structure. And I'm going to need to keep track of 2 things, the head and the tail. Okay, so integer head and tail. And there's a few approaches I could take to this. One way, so let me draw my array. One way to do this would be, okay, we're going to put the tail, let's see, we're going to insert the tail. So we'll put the tail here. And so I'm just going to insert numbers in order so it's easy to keep track of. So we're going to insert the number 1 right here. And then we're going to insert the number 2, so I'll put that in the next location, and then the number 3 in the next location. And when I remove something from this queue, what's the first thing I should remove?
Tail.
So a 1, right? So I should remove this, so I could say, okay, if I'm going to remove, I'll take that 1. There's the first thing that was in the queue. And I'll take all this other stuff and move it up. And now if I want to remove the next thing in the queue, it's a 2. So I'll remove that, and I'll move everything else up. And now if I want to add more stuff, I'll just keep putting them in successive locations. So there's my 4 and my 5 and my 6. Remove the first thing, move everything up. So there's a 4, 5, 6. And now if I want to add a 7, I put that in there. So my tail is basically the number of things that are in my array. Right, it's telling me how big this is, so I know where to put the next thing in. And my head is always up here. So this is the grocery store checkout type of queue. The back end of it, where people come in, that moves around. More people come in and it gets further and further out into the produce section. But the head is always right here where the checkout stand is, right? And that's kind of what we're mimicking here. We're always pulling off from element 0. And when we put new things into the queue, we just put them down here at the end. And this is a really inefficient way to make a queue, because every time you remove, you've got to shuffle everything up. In the store, that's a parallel process. Everybody moves forward 2 steps at the same time, so it doesn't take long. In an array in a computer, it grows as the size of the queue grows. It takes more time. So that's not how we want to implement this. So instead of always removing from element 0, we actually let the head of the queue move around. So we're going to have 2 integers, head and tail. And I'm going to draw my queue like this. So there's the 10 elements of the array. And I'm going to initialize my head to 0 and my tail to 0. And I'm going to draw them like this. Okay, so we insert at the tail, we remove at the head. So first observation, there's nothing in the queue right now. And how can we tell that there's nothing in the queue? Because there's always stuff in the array, right? So what is it about this setup right here that might tell us there's actually nothing in the queue?
Tail is 0.
Tail is 0. There's something else we can say about this situation that's even more powerful than tail equals 0. Tail and head equal each other. And that's going to be what we actually use to know that the queue is empty, because the tail is going to be able to move around, and we're going to see in a few minutes that we can still have an empty queue even though the tail is not 0. But if the tail and head are equal to each other, that's going to mean we have an empty queue. So if head equals tail, then the queue is empty. Okay, so let's insert a 5. We insert at the tail, right? The tail is equal to 0. We just write the 5 right here at index 0. That's pretty easy. We got one more thing we have to do. Increment the tail, because right now if we insert something else, it would also go at location 0. So insert 5. What are we doing? Copy. So q bracket tail equals 5, and then increment the tail. So tail becomes 1, and now our tail is pointing right here. Okay, let's insert a 10. What do? We put the 10 right here. Why? Because that's where the tail is. So same thing, q bracket tail equals 10, increment the tail. So set the tail to 2, and now the tail points right here. So inserting is easy, right? We just copy it to the element pointed to by the tail, and then increment the tail to point to the next location. So suppose we want to remove. So where's the first thing we should remove? What index in the array? Yeah, it's index 0, which is where the head is. We want to remove the 5 because that's the first thing we inserted. So to remove, we just return Q bracket head and then increment the head. So we return a 5 and then we change the head to be equal to 1, so the head's pointing right here. If we say remove again, what do? We look at Q bracket head. Head is 1, so Q bracket 1 is 10. 10 is the thing that we're going to remove. Increment the head once more. Head is equal to 2. And now head and tail are equal to each other. The Q is empty again. Yes?
Just a formatting question. Would it be possible to put H++ inside the brackets?
Absolutely. So we could return Q bracket H++ post. All right, so Q is empty, head and tail are equal to each other, but they've moved down in this spot. Okay, the store and retrieval operation's extremely efficient. We don't have to shuffle anything around in this array. We simply write into this index and we bump up the index. Or we read from that index and bump up the index. So this is sometimes called a circular queue. And it's circular for the following reason. If we do this enough times, if we insert a number and we remove it, the tail and head will move down to here. If we insert another number, tail moves here, and we remove it, head moves here, right? These tails and heads are moving their way towards this end of the array. What happens when they're sitting over here at the left side, when they're both equal to 9 and we insert something? If we insert, the tail is going to get incremented to 10. And if we try to use location 10, we're going to get a seg fault, or at least an error. So suppose that head equals 9 and tail equals 9, and we insert 42. So we store 42 at Q bracket 9, and we increment the tail to 10. And we're setting ourselves up for disaster. What should we do? Yeah, roll back over, set the tail to 0. And it's like this end of the array is connected to that other end. So if we go past here, we just sort of come back here to the beginning. And the same thing happens with the head. If we remove something from here, move the head back down to this location. And if you work through this on a clean sheet of paper and maybe a smaller array, like 4 or 5 elements, you'll see that all of this still works consistently, even if you wrap around and you go back to the beginning. And so your queue might, for example, occupy these locations. And this might be, let me just make sure I don't get this wrong. This might be the head, and this might be the tail. And in this case, the index of the head is actually bigger than the index of the tail, but it's really not, right? Because it's wrapped around. And so when we remove, we'll remove that and that and that and that. And if we keep inserting, we'll keep inserting here. So this works. The one small oddity here is knowing when the queue is full. And we can work through that tomorrow because my picture's gotten really messy now. But But it'll turn out the easiest way to deal with a full queue is when the head and tail are almost the same, but not quite. We're going to call it queue. We're going to call it full. And that's going to happen when we have 9 things in our queue instead of 10. It's just a little edge case, but we'll work through that tomorrow. All right, so we'll continue queues tomorrow, and then we'll move on to stacks. Actually, and tomorrow, remember, we're going to do a GDB exercise in class, so bring laptops or devices, and we'll do the quiz as a group.